PhD in biophysics in Oslo. This is my 8th tournament I attended. Thank you. And now we would like to ask the teams to introduce themselves. So we can please start with the reporters here.
Good afternoon, ladies and gentlemen. We are a team of Belarus, and the members of my team is Ivan Belesnikov, Anna Shamber, Elizabeth Smelkova, and Timur Beziev, and my name is If with love to everyone.
Hello, we're Team Mexico. My name is Antonio. My partner here is Sofia, Santiago, Tania, and Chris. Thank you.
Hello everyone, my name is Dave from Team Canada. Teammates are Hartley, Jason Jones, Andrew Merrin, and Raymond Lin.
Thank you. And last but not least, we would like to thank our wonderful flight assistants who's going to assist us in timing. Would you like to tell us your name?
Okay, so I'm Nico Hudson.
I'm Larissa Petruo.
And I'm Andrew Brastovitz.
Thank you very much. Thank you very, very much. So I would just like to remind that we would like to see who is going to be talking in each stage, but you have right to decide it if you want to only a moment before the person starts speaking. So if you know already who's going to be your opponent, who's going to be a viewer, you're very welcome to write it down to make our life a little bit easier if you write it straight away, but you don't have obligation to. You can, but just be sure that the name is on the board before the person starts speaking. Okay? Everything is clear at this point? Great. So we can start, and we can start with the opponent team challenging the reporters team, and they have 1 minute to choose the time. Can you please start the time?
Hello. Can you provide for us the solution for problem A, please?
Problem 8.
That's Sci-fi Sound.
So the team has time to decide if they accept switch the messages.
Okay, register.
So the problem number 8 was accepted, and now we're going to have 5 minutes for preparation. I'm sorry, I have a look at it. I'm sorry, we can discuss on the end of the very sorry about that. more minutes. Half of a minute more, sorry. For preparation.
So I'm ready.
Okay, we can start whenever you're ready.
Good afternoon, ladies and gentlemen. My name is Beziev. I'm a representative of team of Belarus, and now I'm glad to present to you my solution to the problem number 8, Sci-fi Sound. So we start from the problem statement, and it says, tapping a helical spring can make a sound like a laser shot in science fiction movie. We should investigate and explain this phenomenon. So we start with the description of our experimental stuff. It consists of a spring that we have done for ourselves, a tripod, a cup, and a microphone. And with the help of a special program called Sony Visualizer, we obtain the experimental data. So now you can see the demonstration of the effect, but unfortunately it doesn't work. Yes. From the side of the cup, and here's the same from the front. This sound indeed is really similar to the laser shot. So let's explain this phenomenon qualitatively. The reason for sci-fi sound appearance lies in the fact that high frequency waves spread faster than the low frequency waves due to the acoustic dispersion. But why we can obtain different frequencies separately? The simplest example of geometric sound dispersion is dispersion in bending waves transmission in rods. So in bending deformation, the elastic coefficient increases with the bending section length decrease, which is determined by the bending wavelengths in our case. As a result, effective elasticity and wave velocity increases with the decrease of the wavelength. In other words, with increasing of the frequency. So the bending wave velocity is proportional to the square root of the frequency. And here you can see spectrogram of our experiments. And that's why we see this hyperbolic view. And now let's get back to our setup and explain the usage of the cup. We have conducted experiments both with cup and without it, and came to the conclusion that the cup only enhances the sound amplitude and concentrates the sound in a narrow beam. And now let's turn to the theoretical description. Bending waves are waves represented by bending deflection in spreads, spread in rods. Well, technically, on those waves, which length is much bigger than the width of the rod, may be called bending waves. So, from Tikhonov and Samarsky, the equation of mathematical physics, we use the following equation, from which we can obtain the relationship, this formula. This is dependence between velocity of the sound and sound frequency, where ρ is material density, E is Young's modulus, and I is radius of duration. But what does I stands for? Well, we have considered a spring rod cross section. As I said, we made our springs by ourselves, so our cross-section area was cylindrical. The duration radius is determined by the square root of the ratio of second moment of area divided by surface of figure. And the second moment of area may be calculated using the first equation. And now let's do this. Integrating the first equation over the area and take it into the account Pythagorean theorem, we can get the second equation. The radius of duration and second moment of area are connected by the formula number 3. So substituting everything, we can get that radius of duration is equal to radius of our spring divided by 2. So using previous formulas, we built a mathematical model in Morphium Mathematica. So here you can see the two spectrogram. On the left, the mathematical model, and on the right, our experiments. So sound from what we got in experiment and as you can see, the sounds are similar. And now let's move to the experimental part. The dependence. Here you can see the dependence of amplitude of sound to the time. The amplitude dumps with increasing of the time. Because of the curve, we have sound. Because sound has losses to the environment. So it doesn't make sense to compare frequencies with the change of the time. Because according to the acoustic dispersion, we observe all frequencies. So that's why we'll investigate spread velocities. And what does this spread velocities mean? On this slide, you can see these white arrows. And these arrows mean they show the time necessary for the wave to cover the distance of two screen lenses to the one side and came back. So knowing the time and the length of the screen, we can obtain the velocity for a certain frequency. And this is the parameter that we have chosen to investigate. To move on to the parameters of our systems, which we decided to investigate, and they are cross-sectional area of the rod, YP number, prolongation of the screen, and material. Here you can see spectrum for different cross-sections. And as you can see, with the increasing of the cross-section, the velocity for certain frequency decreases. It is explained by the fact that radius of gyration depends on cross-section area. So with increasing of cross-section, the velocity for certain frequency increases. And here you can see how exactly this radius of the screen depends on velocity. With the decreasing of YP number, we only change the length of the screen rod. So as I said before, only the cross-section area and parameters of the material, such as velocity and Young's modulus, influence on the such as density and Young's modulus influence on velocity. So also we prolongate our screen for 1 meter, 2 and 3 meters. And as you can see, there is no any dependence on the prolongation. It is explained by the fact that with the change of the length of the screen, the length of rod does not change. And that's why prolongation of the screen not influence of the spreading velocity. So velocity does not depend on screen length due to the fact that with increasing of the screen length, the rod length stays constant. So after all of this, we decided to compare spring of different material. On the left you can see a steel, and on the right you can see a plastic sphincter. It should be noticed that in both spring the acoustic dispersion may be observed. But, so there are all frequencies. But in a plastic spring, the wave damping ratio is much more bigger than in the metallic one. So that's why we don't observe and hear the secondary frequencies, as you can see on the left. As to get the full frequency spectrum, we hit our plastic sphincter near the microphone. So that's why you can see all these spectrums there. That's why the result looks like a line, but not hyperbolic. This is explained by the fact that because the distance is small, which leads to the fact that high frequencies and low frequencies come almost at the same time. And now let's get to the conclusions. The effect is observed due to the different spread of the wave propagation in the screen. And we have presented convergence of the theory with experiments for cross-sectional area, for the YP number, and for the prolongation of the screen. Here you can see some references that we have used in our report, and that's all. Thank you for your attention.
Thank you very much. Now, opponent will have 2 minutes to ask questions.
Okay. First of all, I would like to ask. You mentioned that you repeated the experiment with different type of
Yeah.
different type of springs. You mentioned plastic and
And aluminum.
aluminum. Is there any other type of spring that you use?
No, we don't use the other types of spring.
Okay. Also, you mentioned that that you actually heated the plastic spring by one side. Is that right?
Could you repeat this?
That you mentioned you heated the plastic spring.
Yes.
Yes. But I actually believe that you didn't show the comparison. Or is there anything?
The comparison between in the sound.
Yeah.
This sound is very small, so I show you spectrum for these two different types of thing, but I don't have the sound from the plastic one.
Okay. And another question is, did you measure in any way the amount of energy that you were using to heat the system?
No, we didn't do this.
You think? Well, that's fine. Thank you.
Thank you very much. Now, opponent have 3 minutes for preparation. We will need to start soon. Yeah. Now I have maximum 4 minutes for your presentation. Okay, your time is running.
Okay, well, my name is Ruiz. I'm going to be, first of all, I'm going to be your opponent today. I really want to thank you for your explanation. You were, I believe you did really good, and I'm really satisfied actually with your explanation. I believe you chose really important points. However, I believe there are some points that we could put in a bit more. First of all, these are the relevant, as my point of view, these are the relevant parameters that they are asking us: tapping, helical spring, and laser shock. These are my general observations. I believe you had a really solid hypothesis. You really had in mind what it was going on during the experiment. However, I believe you could have gone a little bit further into the explanation of the entire phenomenon. The theory, I believe it was really good. You had really good. I believe you had a really solid model. The experiment, I believe you have a bit. You can improve that a bit further. There are some points I believe that could affect and could be improved during the experimentation phase. And that leads to the calculations. You had a really solid model, but maybe if we take into account those other parameters, maybe we can, I don't know if we could expect on any other kind of result. And well, this leads to the conclusions. Even though you had a really solid theory, I believe this may be affected by the calculations and the experiment. First, theory. I believe, as I told you, I think you did really good and you had a really solid theory. I was really impressed as you really showed perfect comprehension of the acoustic dispersion, which I think is key for the resolution of this problem. However, I believe you could have tried with different variations for the solution. Since you only, as you mentioned, you only tried with a plastic spring. Well, you tried to vary the heat. That's also really important, and I believe that's also worth mentioning. But I believe that it's worth to mention also sound interference and sound decay in the theory. We can touch that in a second. For the experiment, well, I really like the fact that you tried the experiment alternating the length of the actual spring. The fact that you did your own spring, it counts a lot because it allows you to actually understand how it works. You understand the cross section pretty good, and as I said, you could have tried to modify more variables, and the force, I believe that's kind of important. Even if the problem says tapping, how does if that can affect the problem in any way? Well, that's it.
Thank you very much. The discussion can start now.
Yeah, well, as I was mentioning, first of all, more variables. I believe that, well, I'm not sure, but as you said, you tried with a plastic spring and aluminum spring. But did you ever consider trying with any other type of spring?
No, we did not do this because we have only metallic one and metallic. So we can obtain the dependence on frequency from our theory, but we don't connect them for other types of spring.
Okay, and I say aluminum. You said you fabricated your own aluminum spring,
Yes.
but did you try to vary, I don't know, the diameter of the spring?
Yes, as I said, I made a 5 spring, so with different diameters and with different lengths of the spring.
Yeah. Can you show us again the slides where you were showing the results for each of these variables?
Which one?
Yes. Can you show, for example, here?
Yes.
But can you repeat the values for each one, or well, the
values
parameters
for
you will
each one.
change it for each
There
one?
for each one you can see on this slide. This is 2 millimeters, 1.5 millimeters, and 0.5 millimeters. This is the radius of the spring rod.
Yeah. And another thing, okay, you said you fabricated springs. You alternated the diameter, the length of the entire spring. But what about the length in each coil of the spring?
Would it be
Well, I know this as a coil actually, like each one of
this
the.
diameter?
Yeah, I mean this length. I'm sorry.
This length?
Yeah.
Well, this length does not depend on the velocity propagation, and I show you on this slide. I show you this on this slide. You can see prolongation of spring, we used the same spring, we just prolongated it. So it was first like this, and second like this. And as you can see, there is no change.
There's no difference.
Yes.
Okay, that was a huge question of mine because as far as I know, helical springs can be used for compression when there is a really super, really wide length coil spring, but it can also be a spring used to for extension. So I was expecting it to affect in any way whether or not they are more compressed. Each of the coils is more compressed between each of the coils. Did you ever try, or did you have any idea of trying this problem in a vacuum?
In vacuum, no, we did not use because we do not feel it sound.
Okay. And which material were you using to heat the spring?
Which material? We use a pencil.
Huh?
We use a pencil.
A pencil.
Pencil.
Okay. Do you think it can affect the
No,
material you are heating it with?
No, it will not affect the material.
Okay. And the force, what about the force?
We beat with different. The force will not influence on spreading velocity. It will influence only on amplitude of sound.
Okay. And can you show me the slides where you were presenting the difference between plastic and metal springs?
Yes, this one.
Yeah. So as far as I can see, the plastic was not showing much results, right?
Could you repeat this?
Plastics, you cannot see a real.
No, we can observe all this acoustic expression. We have all frequencies in this slinky, but the generation is so high that this amplitude, that's why this amplitude is so low.
Okay. And another question. The problem states that you need to find whether or not the slinky sounds as a laser shot. But actually, I don't remember if you ever mentioned it. What characteristics actually a laser shot has? Like, how can you compare it, or what's your what's the base? How could you describe a laser shot?
Well, I think that laser shot is a shot when the low frequency spring slower than the high one, and that's why we can observe such T. So first we can hear the high frequencies, and after this we can hear the low frequencies. So the spectrum will be the same.
Okay, because in both cases you can see the sound dispersion.
Yes.
In both types of springs, but one of them is clearly different than the other. Do you still describe the plastic spring as a laser shot? The sound
Yes,
it
of
makes?
course. It will also be like a laser shot, but this amplitude of sound will be so low that the amplitude of sound will just be low.
And the amount of energy that you needed to create the effect, did it change? Like you were using more strength at the time of hitting this plastic spring?
Spring. Yes, we hit it with the maximum strength as we can, but as you can see, we just change this material.
So it does affect the strength that you're using at the time of hitting the system?
Strength affect only on amplitude of sound.
Yeah,
So,
but
so if we will hit a bit smaller, this amplitude will be much more lower than here you can see.
okay. And another question, you were placing the microphone like right to the end, right?
Yes,
Right to the end of your system.
we have a cup and spoon, and here and here was the microphone. So we tap here, sound will up again.
And did you ever try to leave the sound wave propagate and measure it on the actual plate where you hit first time?
Well, if we will do that, what will be if we hit
Yeah, probably. What if you hit? What happens if you hit on any other side of the
Well,
spring?
it will not influence, the velocity will not influence on this. So, you can see, I can draw a spectrogram. For example, if we will hit there, first of all, we will observe this line, because the time when all velocities came to our cup will be the same, and that's why we'll observe this. But after this, wave will goes to the other side and back, and we'll observe these lines, curves.
Okay, but you were using. What I don't do not fully agree is that they are not coming actually back to the same point, so you can actually found the sound. Well, I mean, so you can use the spectrogram. I believe.
It means that it doesn't depend on where we will hit there. This on this side of the screen or on this one.
Yeah, but what happens if you hit in the middle?
The spectrum will be always the same.
Exactly the same, but you never tried it, right?
Yes, we tried it. As I said to you before, on this, the velocities for certain frequency will be the same, but the first curve, if we will hit closer to the cup, the first curve will be more look like the line.
But as far as I know, if you hit in the middle, the sound waves will be propagated in both directions. What will happen in the middle when they cross again?
Well, I think that if we will do this, we will observe the different echoes and noise in our system.
I don't think it might be echoes, because echoes are always separated by some time, and this is more something like a reverberation. And that's actually a huge question of mine, something I think we could change, we could take into consideration, because if both sound waves are propagated in different directions, by the time they cross again, they may form, or at least that's what I believe, they may change the effect, or at least make some difference in the spectrogram.
I think that no, it will not change the effect. So if we will hit there, some frequency will come to this side. So we will observe this line, and they will come to this one.
Yeah, that is if you have the microphone here, but what if you have the microphone right under the...
But we can't put our microphone there, because the amplitude of sound will be so low, and we will not just hear this sound.
Why not? I mean, if you have a hanging spring, by the time if you hit at this point, it will start vibrating. It will still be under movement. Sound.
Sorry,
sound waves.
do you have short answer to this question?
No, we did not conduct this kind for this case.
Sorry.
Thank you very much. Now, opponent have 1 minute to summarize the discussion.
Well, I'm really thankful for the opportunity we had to actually clear some of the doubts I had. I'm really impressed by some of the actual improvements that I was clearly, by some of the points that I clearly not noticed at the beginning, because I was able to clear them at this point now. I still believe that there are some things that we could change, some variables that we could alter, so that the experiment will be a bit more complete, so that we could actually see all the possible differences in the experiment. But as far as I can notice, I believe that these variables may not affect completely or drastically the experiment, but I really believe that they may affect in some way the phenomenon. So I believe that we could improve the model like that. Thank you.
Thank you very much. Now we will have questions from reviewer. Sir?
So first off, did either of you consider a rectangular cross section?
No, cross section.
Yeah, rectangular cross section.
No, we did not our theory built only for cross-section, cylindrical cross-section. If you,
I'm sorry, how about the...
No, actually not, because the experiment was asking for a helical spring.
So do you guys think that having a rectangular spring makes any difference?
well, I think that if we will use rectangular spring, the radius of gyration will be not like this one.
Anything
So,
else?
what?
Adjust the radius of gyration.
Yes.
How about what do you think?
I believe it could affect, because you're actually, by doing that, you're affecting the total width of the spring, and you may be affecting the diameter in some way. I also believe that it may affect, because you're also changing the area of the wave sound propagation.
Okay, so in addition, how about, so I noticed on your spectrograms you have multiple lines. What are those? Why are there multiple sounds?
Okay.
So what are those actually? Just what are those multiple sounds?
Well,
Just like a quick answer.
we have a spring, we hit there. So,
Is it the echo?
yes, it
Okay.
just.
And how do you calculate velocity?
Well, the velocity for certain frequencies, as I said before, remains constant. Here you can see our spectrogram, and this distance is always the same. So,
And on your graphs, what are your error bars?
error bars. Yes. Well, just a second. Our error bars was about
No, I mean like what value are they?
value about 10 gigahertz.
Just as constant?
Ooh.
Or like how do you calculate those error
Well, we just can't calculate this error bars because we hit every time we hit the different
Or
source.
do you just have an arbitrary value?
Yes, we don't.
Okay. So also do you have any frequency? Do you look into like frequency time relationship at all?
Frequency time relation.
Or like did either of you?
Frequency time related.
Yeah. The relationship between frequency and time, like frequency time.
I mean, I don't know if you can see
Frequency time relation.
Okay.
The spectrum
So what do you think the graph would look like?
frequency and time. This spectrogram shows us on the y-axis we have frequencies, and on the x-axis we have time.
So how about in terms of how do you calculate time zero?
Time zero.
Last question.
We don't calculate time zero.
You just assume it's the zero on the left.
Well.
Or when you hear the first sound.
Well,
that seems like.
as you can see, we have some time there. So this 0.2 second.
Sure. Can I get the?
Okay. No, you don't have any more questions. Thank you very much. There are 2 minutes for preparation now.
begins. Tapping a helical spring can make a sound with a laser shock necessary to investigate and experiment. Alright, so we believe that the tasks for these two problems are first, construct a well-controlled experiment. Then we believe you have to analyze the transverse waves that are occurring in the beam, which is how we essentially model the spring. And then third, we have to discuss the importance of dispersion and how that affects the sound that we hear. And fourth, experimentally verify the theory by varying various experimental parameters. Alright, so a quick summary of the reporter. So they have a fairly good qualitative and some quantitative understanding of the problem. And in terms of their analysis, they began with a qualitative explanation and then a quantitative model and some experimental data. And then you can see, so with their experiment, they had a setup with a cup and a microphone mounted with a spring, and then they did their experimental verification. So in terms of the reporter, we thought they had a very thorough qualitative analysis of the dispersion. Also, the visual and audio representations were quite interesting and good to look at. In terms of next steps, we believe that there was a fairly limited theoretical model because they only analyzed the one cross-sectional shape, which was a circle. There was no discussion of the different types of dispersion that could occur for a rectangular cross-section, for example. Assumptions of their beam theory that they used were also not stated, which is important. And also the lack of experimental control, especially with regards to manual payment. So in terms of the opposition, they had fairly general observations of the different sections of the theory. They had the theoretical strengths and weaknesses, which we thought was good as well. And lastly, they discussed some of the experimental strengths and weaknesses. So in terms of the opponent, we believe some of their merits include the good visualization of the evolution of their opponent's theory. In terms of next steps, we believe there's a lack of detail and nuance in their presentation, perhaps understanding why the certain points they're saying are true. Again, some of the relevant points were discussed, such as vacuum, which would not produce a sound in a vacuum. Also, some incorrect theoretical predictions, as I'll discuss on the next slide. So in terms of the discussion, they discussed the dependence of length on velocity propagation. So the opponent said that the coils that are more compressed maintain velocity, and the reporter responded that velocity propagation does not depend, and I agree with this, since we also found this through our own experiments. And the equations do not depend on the angle, the incline of the spring. So in terms of the force applied, again, so the opponent believed that the force should be controlled and measured, and the reporter responded that the minimum force is required to reduce the sound, rather than that it only affects the amplitude. And we agree with both of them that the force affects only amplitude, and experiment should be able to measure and control the circumference, which as we talked about earlier. So in terms of the role of the striking position, again, we agree with the opponent. Because the striking position is going to produce waves on both sides, and that can also produce interference, which may also cause additional issues with the data. And also with regards, we believe we also believe that with the striking position, that what has to be done in their experiments is that it also has to be controlled, because in that scenario you cannot have echo, and because the echo will produce that interference. So for example, sticking a piece of clay towards on the end of the spring could solve that issue. So in terms of some of the general suggestions for the reporter, we believe that the experiment should be concerned with more control. For example, constructing a mechanical hitting mechanism. In addition, the theoretical model should also be expanded to account for the other cross-sectional shapes, such as rectangles, since we believe there's a lot of interesting observations that can be found there. And lastly, we believe that that the reporter has to demonstrate a more thorough understanding of some of their experimental data. As we noticed, they didn't really understand where the T0 was for their spring, when in that case it should be actually when the spring is.
Thank you very much. Now we will have 2 minutes for concluding remarks from the reporter.
Well, I want to say thanks to the opponents and to the reviewer, and want to mention a few points. Cross-section of the rod of the spring, not the cross-section of the spring itself. And if we take rectangular, we will just change the length which wave travels through. And the second one, striking mechanism. We decided to investigate only velocity and frequency of the sound, and that's why it doesn't matter for us how we hit our spring, because it influences only on the amplitude. So that's all. Thank you.
Thank you very much. Now we have time for jurors to ask questions to clarify what we're going to do. Please.
What is the writing number that you slide it would be true. What is it?
Okay, just a second, please. YP number is a number of these wipes. For example, 5 or 10.
I have two. You want me to split them or do them both?
Could you start me first?
I have a question for the opponent. So one of the things we have to judge on is the reporter's contributions, something new on this particular topic. You've read the literature, I'm sure. After you've looked at his report, is there anything that you felt like he added to a better understanding of this topic?
Well, I actually believe that the fact that he hit the system when he tried with the plastic spring, that I believe that was something really innovative and really new that I'd never seen before.
Review?
I think just in general, it was, I think personally we didn't actually test plastic ourselves using this separate metal things, and I think that's really interesting. Also just like I thought it was a good summer, lots of good quality of explanations of the theory, which made it very easy for you.
For the reporter, real quick, you said earlier the high frequency waves travel faster than low frequency waves.
Yes.
Can you briefly explain to me why that is?
Okay, as I show you there, if we increase the length, the wavelength also increases. So k, which is equal to p divided by lambda, 1 divided by k1 is less than 1 divided by k2, which leads to frequency 1, which leads to, if we will take the length more, the more length of the spring, its frequency will be more than the small one.
Thank you.
I would like to ask, in your graphs where you presented your experiments, you had a red line. Was that a theoretical prediction or was it fixed?
This is theoretical prediction.
With no free parameters?
What do you mean about free parameters?
Did you fit it or did you plot it?
I don't fit this. So
Okay.
you can see there, we have Young's modulus, just density. Young's modulus is about 2000 gigapaskals, right? Material density is about 7,000 kilograms per meter squared, and the radius of duration is I variate this in our theory.
Thank you. This next question.
Please show your slide 6 again.
6. This one?
What is B in this?
B. It is amplitude.
Amplitude. So the velocity depends on the amplitude, yeah?
Not. Well, I can.
Explain it, please.
I can show you example on the spaghetti, for example. If we want to among spaghetti, it is much more easier to bend it than to bend the small one. So that's why. Do you understand?
Yes, so your answer is that it does not depend.
Yes.
That's your answer. You don't need to explain it. Any more questions for the please, yeah.
The opponent, actually, the reviewer asked the question, or the opponent asked the question, but somebody asked the question, I don't think we got an answer. How did you measure the velocities of the wave propagation?
Okay, just a second. Well, I have a spectrogram, so I know the length of my spring. It was about 10 meters. So I know the time when the sound velocities came to the one side of the spring and came back. So using the formula, we obtained the velocity.
Thank you.
Thank you very much. Now we will put down our grades for all of them. so we are ready to present the marks. So first we will, I need to write it down, sorry. First we will see the marks for the reporter. Before we do it, could you please tell me which order would you like me to read it? Who is first in the list?
Either way, we are prepared to go out either alphabetically or in the order that you want.
Okay, so can we just say in the order we start in this corner and can move that? Is that okay for you? Can you see all the names?
Yeah.
Okay, perfect. So we will need the mark for a reporter now, please. And that's 5, 6, 5, 5. Now the mark for the opponent, please. Now, 5, I'm sorry, 3, 5, 6, 4. And now the mark for reviewer. That's 5, 7, 6, 9, 9. Thank you very much. So we will explain our marks. For reporter, it was we agreed pretty much. We only had 1 6, which is I think within the But if you would like to say a few words about that.
Well, actually, my 6 is my partial grade is a little bit lower than first part is a little bit lower than 3, so I make it 3. And the second part about the discussion is 1.5. So adding up is 5.5, rounded to 6. So actually, I don't think I'm away from the 5.
No. So it would be very big coincidence if we all have exactly the same one. It's very close. But anyone would like to comment on the report as well?
I think we're pretty consistent in terms of your work. I'd like to just give you a couple suggestions about improving, for future fights. In your conclusion, you only had a 30-second summary of your work. One of the things I would stress a little bit is to really be able to cycle back and really put an exclamation point on your contributions so that our lasting memory is all the good things that you've done. The other thing, and maybe it's just my ignorance, that question, so I was vacillating again between 5 and 6, and the question that you had versus the higher frequency waves traveling slower than faster than the lower frequency waves. And my colleague at the end asked you a question that I don't think you gave a particularly good answer to. And so one of the things that we have to do is, if you answered your questions poorly, we take off points. And so, I was deciding, I didn't know it well enough to know, but I wasn't particularly happy with your answer. So when I was sitting there between 5 and 6, I moved down to a 5 instead of my period moved up to a 6. Down to a 5.
Thank you. Yeah, sure.
I think I can give some comment because I think the problem has to explain and investigate the phenomena. So I think one of the scientific way to explain is that to explain how if we can achieve a situation where the sound hears not like a sci-fi sound and away from that, and try to find out that situation, then reverse that process, you can know what's the key point of the sci-fi sound. So I think that's the missing part of your report. So otherwise, the other parts are pretty nice. So I think if we can add on that, everything will become perfect.
Thank you very much. Now for the opponent, we had a little bit more spread. So can we start with the three, please?
Sure. I thought this was quite a weak report, and then that meant that there was a wide range that you could have gone with as the opposition, right? There was a lot of material that you could have really dug up and talked about. And so I thought considering that, the treatment was quite shallow. For example, a few things maybe you can work up next time. You used a lot of maybe sort of empty words. You know, so you kept saying things like, oh, it was like a good explanation of the theory. Well, I was sitting here thinking it wasn't a particularly good explanation of the theory. And so I think sometimes you were almost too generous in your praise, and that made it difficult to tell when you sincerely thought there was a really novel contribution, and when you were just sort of, you know, being friendly. And so that's one thing too. I would like to have gone back and dug into some more of the fundamental physics, so getting into how the waves propagate, like all of the things that were a little bit rushed in the presentation. Suddenly there was a quantitative model introduced that you didn't engage with. And so I gave you sort of, reasonably good points on some areas, like you talked about controlling the experiment a little bit more, but there was just in no particular area the depth that I would have really expected to see from an international level to give it any more benefit.
So gave before, so I'm on the same level, because I couldn't give you much points for the presentation at all, because you were saying this was good, this was good, this was good. It doesn't mean anything for me. I want to know what you think about this. The equation for the velocity was very well derived, and we agree with using this principle for derivation of this. Actually, Martin was just talking about that if your captain was of the meeting. Like, he was explaining that we need a specific points to give you marks. Then for the, I feel like you were fearing the theory. If the theory wasn't crystal clear, you shouldn't start your questions with what other parameters could you vary. This really sounds to me like, I don't know, what should I ask, so a little bit. So it's a lot of time pressure at the moment, but the questions, the prioritization of this question, and start with something which is relevant from the physics point of view, not just from the design of the presentation, would bring you so much more point. And then discussion, unfortunately, it's hard to say whose fault it was, but you pretty much just went around 2 points, right, without a presentation and where to talk. Well, there were so many things to discuss on the more fundamental level, so for the next time. But we also had 6, so we have some more positive points.
Well, I'm just a positive person. So a couple of just constructive points to help you do a better job of this tomorrow and the next day. Using your time well and effectively, they've been hitting on, is very important. So when you were asking your questions in the beginning, you got to a point where I think you had just run out of questions to ask, and then you just started mixing in things that I don't think were very helpful for any of us to understand their report better. And so cultivating that skill of being able to probe deeper into the problem is important. As far as your opposition speech is concerned, they touched on this business about using words like good or excellent or words that I had written down were the first 30 seconds of your speech were fluff. And what I mean by that, you weren't adding any value, you were just saying nice things about the opponent, being polite, which is admirable. But on the backside, you finished at 3.5 minutes. And so basically you left a minute worth of your time, you didn't use it. And so that's your time to really, let your big brain shine and let us know what's rattling around in there in terms of this, right? So you want to construct your arguments so that you're using that time as well as you can. So last little thing, so I was kind of keeping note of your questions, and eventually during your discussion, you asked them about running this experiment in the vacuum. Now, the alarms went off in my head. As a leader, I'm going, he's run out of questions. He's just throwing something up here to keep talking. I don't know how the heck you'd run that experiment in the vacuum. And even if you did, the result would be trivial, right? And so I put a little note in my thing that he's run out of steam. We've still got 5 minutes to go. What's the rest of this going to look like? But you actually rebounded and you started talking about the qualitative, how did you qualitatively measure a laser shot, which I thought was a good question. You started to get into detail about, they didn't really give us much data other than a couple of graphs, right? They didn't give us much data to investigate the theory. And you finally got into that business about, interference, or, if you hit it in the middle, what's going to happen with those kind of things. I think your prioritization was a little off in your discussion.
Thank you very much. Thank you. And we also have points for reviewers, so we can start with the 5.
In my opinion, there were lots of fundamental physics in his report, and the opponent didn't discuss the situation. So, and you didn't show us that what to do with the situation between the report and the opponent. Only special details, but so little about fundamental physics. So,
So I obviously disagree. I gave you a very good score. And so I haven't been, I don't know if I've been doing it, and he may have a different impression about what the review should be, but in my case, I thought you added value to me to understand the differences between these two folks. I thought you added some nice little thing that you kind of stumbled on this whole issue of the error bars, which I think was kind of an accident, and then you picked at it and realized, what they were going with. You also got into those, how they measure time 0, right? Which I think is a non-trivial question, and I thought, you're kind of zeroing in on that, was helpful. You also discussed about how they calculated velocity, right? So these were questions that were running around in my head, and you tried to get at them. The one thing that you didn't do was, I didn't feel like you added much of your own contribution to their work. But I gave you a 9, so you really can't complain.
Yeah, well, I have to disagree a little bit in this part because I actually very much appreciated that you did not join this discussion, like what other parameters could we have talked about if we would talk about. I think it was a lot of that in the discussion, and I really appreciated that you kept distance and you told us what was happening and you explained what do you think about that, because I think many teams would just kind of get along and try to talk about the same thing that they were talking during the discussion, which would not be good at this point. So I very, very, very much appreciated your questions, like exactly the same situation. You just keep asking questions like that's exactly what I wanted to ask. And you uncover some very important points which wasn't mentioned at all, and you wasn't afraid to start with a theory, which I also found very, very important. And then I did agree on your presentation and your opinion about what you think about presentation as well. So I think it was really, really good.
You also agree?
Can I make one more comment?
Absolutely, yeah.
Because I was sitting in between.
Yeah.
I get the impression from the questions you asked that you understood the most of everyone here. But to Andre's point, I think you could have been more direct in that. Like, I think you can hit straight on the head that the theory wasn't adequately covered, that there was a lot more physics that could have been had here that wasn't had. Whereas I had to sort of infer that from the questions that you were asking. But it also then made me doubt your prioritization. Because, there are a few things which sort of maybe you're trying to suggest something, but to me felt like you were avoiding the direct issue, which is there's a lot of physics that we haven't touched.
Thank you very much. If you have more questions, however, we will be happy to talk to you more. Otherwise, we will have a 10-minute break and we will start 40 past 4.
They did a very nice